Today you'd learn about hardness tests. Uh, so before that, we need to learn about the very property that we are trying to test. Mm, if we talk about uh, different properties that we have so far looked into in the laboratory class since the last semester, there would be strength, there would be toughness. So I'm just listing the important properties. So of course there is properties such as elasticity, which is measured with Young's modulus, which is essentially the resistance to elastic strain for a given load or given stress within the elastic limit. Now we are talking beyond the elastic limit, and if we go beyond the elastic limit, then these are the properties that become significant. Now to start with, what is strength? We have already discussed about uh, strength of a material in in the tensile test experiment. Actually, any of these properties can be can be shown in the stress strain diagram. So on the y-axis there is stress, which is engineering stress, which is force, applied force per unit original area, assuming we are still doing an uniaxial loading. And strain, of course, is a change in dimension per unit original length. And for a ductile material, this is what the stress strain diagram looks like. And the ductility of the material is measured in terms of the maximum strain that it can be elongated to before having a fracture. Now, if I draw the stress strain diagram for a brittle material, that would be considerably different and with very tiny amount of plastic strain, mostly elastic strain. And uh, a brittle material doesn't show a distinct yield point. It uh, it simply fractures once it goes past the elastic limit. And and so we discussed this thing that within the elastic limit, we can define the elasticity in terms of the Young's modulus, which is resistance to elastic strain, the kind of strain that you can recover, that is immediately recovered once you unload the component. So kind of strain that is immediately recovered. So let's say a material is loaded up to this point, and if you try to unload, so it unloads certain part of its strain, and that strain is whatever has been the stress before unloading divided by the Young's modulus, and that is your elastic strain, and that is the part of the strain that can be recovered. So that's what is elastic strain. And the part that cannot be recovered after unloading, so let's say if I load along this curve, and when I try to unload, the material follows a curve something like this green line right here. And the part of the strain that could not be recovered is actually the plastic strain. Now, once you are in the plastic domain, first of all, you encounter something called an yield point, which can be representative of both the maximum stress within the elastic limit, maximum stress that a material can have uh, with uh, with solely elastic deformation, and also the initiation of plastic deformation. Okay, actually there are a couple of different stresses, uh, or maybe more than that. So there is yield point, there is elastic limit, there is proportional limit, but those stress values are quite close and can be represented with a single stress value. And for most practical purposes, that can be taken as the yield point. And uh, then of course there is a stress at which the material fractures, but that stress is not the maximum stress in the stress strain diagram. The maximum stress in the stress strain diagram is the maximum load bearing capacity of the material, and that is called the ultimate tensile strength. So we literally use the word strength in naming the stress value, and that quantity can be classified as the strength of the material. Next comes the toughness, which is not a representative of the maximum stress value. For example, this brittle material right here fails at a higher ultimate stress value than the ductile material in the two representation right there. But that doesn't mean the brittle material would be more suitable for different applications compared to the ductile material. As it turns out, possibly the ductile material would be more suitable in many applications, and the reason behind that is this quantity right here, toughness. So toughness talks about not the maximum load bearing capacity, but the maximum amount of energy that the material can absorb without having a fracture. So maximum energy without fracture. Maximum energy that the material can absorb absorb without having fracture. And the same term can be rephrased as the total energy absorbed up to fracture. They basically define the same quantity. Okay, but since we are not talking about a specimen, particular type of specimen, we are talking about the material. Okay, so we have to a material specimen, let's say a tensile specimen, has two parts. One is its geometry, the other one being the material. If you take so if you take both of them, then you have the properties of the specimen.
This material, does it means the composition of the material?
Sorry?
The geometry plus material. Is this material means
Yes. The material means whatever alloy or whatever composition that might be. Okay. So what we are trying to do is we are trying to isolate the properties of the material from the properties of the specimen. Okay. So for example, if I am talking about the property of a component, I can take the spring for an example. When we talk about a spring, we don't talk about Young's modulus. We talk about the spring constant, which is essentially, again, an elastic property which represents for a linear spring, which is the ratio of the applied load to displacement. The definition is very similar to the Hookean definition of Young's modulus, which is the ratio of stress to strain within elastic limit. Okay, but when we talk about not a component made out of a given material, but the material that it is made of, we don't talk in terms of stiffness. We talk in terms of, let's say, Young's modulus. And that's what we do within the elastic limit. And when we enter the domain of plasticity, we talk in terms of other important stress quantities. So we don't talk about force, but force per unit area. We don't talk about elongation, but elongation per unit length. So hence we, talk in terms of the stresses and strains, and most of these properties that we are talking about, they can be directly shown on the stress strain diagram. And next comes the toughness. So if I want to define toughness, so if I want to isolate the property of the material from the, হ্যাঁ বলো।
স্যার বলছি, যদি আমরা স্প্রিং নিয়ে কথা বলছি তাহলে স্টিফনেস নিয়ে কেন কথা বলছি না আমরা এখানে? মানে বলতে চাইছিলাম যে স্প্রিং এর তো আমরা স্টিফনেসটাই দেখি।
হ্যাঁ, কিন্তু আমরা এখানে স্প্রিং নিয়ে কথা বলছি না তো, আমরা তো এখানে মেটেরিয়ালের প্রপার্টি লিস্ট করছি। সো ইউ আর লিস্টিং দ্য প্রপার্টিজ অফ দ্য মেটেরিয়ালস হিয়ার।
আচ্ছা,
ওকে,
রাইট।
for example, when we did tensile test or when we did isort test, we are talking about these properties, strength or toughness. Okay, and actually we did discuss all of this in those classes. If you revisit those lectures, you will see that. But what I'm trying to do here is trying to build a connection between all the different properties. So hardness is a property that we didn't discuss in the last semester.
Yes, sir.
Okay, so we are indeed talking about material, and hence we are talking in terms of the stress strain diagram. And when we are talking about toughness, uh, and so the more correct definition, because it's a property of the material, this should be per unit volume. Total energy up to fracture divided by the volume. So once you so now look at this integration right here. So this is the original volume V0, and this is force, and this is differential displacement that I'm integrating. So basically, if I integrate this quantity, or basically if I give you the area under the stress strain diagram up to the point of fracture, this whole thing right here, okay, so that basically is this integration, that area is this integration, and that integration is per unit volume PDU, which is work done on the specimen. Okay, and therefore this is also the amount of energy that the material absorbs, okay, up to the point of fracture. Now the specimen absorbs up to the point of fracture. Now if you divide that with the volume of the specimen, then you have the measure of toughness. Okay, so the toughness could, so the point is the toughness could be represented using the area under the stress strain diagram up to the point of fracture. Okay, and a related property is resilience that we discussed could be obtained by performing the same integration but within the elastic limit. So this is resilience. Okay, so all of this you will find in the lecture related to isort impact test. Now today we are discussing about hardness. Okay, now hardness is in general hardness is a resistance to plastic deformation. Okay, now you see this stress strain diagram right here. Okay, on the x-axis it plots the total strain. Okay, of this total strain, if the stress is less than yield stress, all the strain is only elastic strain. Once you go beyond go beyond yield stress. So you start developing both elastic strain and plastic strain. Okay, so this total strain is made of the elastic strain and the plastic strain, of which this elastic strain right here is stress divided by Young's modulus. Okay, now now if I take away this strain right here, see, experimentally it is you get basically this deflection from the extensometer and this force uh, from the sensor. Okay, so so experimental data is this displacement and this force. So you can of course have this dimensions, the cross section area and the length, all of those could be pre-measured before the experiment. So these are the dimensions before conducting the experiment, the original cross section area and the length. And so you can calculate the engineering stress and strain, and you have the stress strain data. Now you do not know how much of that strain is plastic strain, but this formula is there to very easily calculate the plastic strain from the elastic part of the curve. Okay, or within the elastic limit, you can very easily get the Young's modulus from the stress and strain values. And once you have the Young's modulus, you can get the plastic strain using this formula right here. And once you have the plastic strain, so this is what you can do. You can plot stress versus plastic strain, and that diagram looks something like this. Now, why does it make a y-intercept? The fact is, when your stress is below yield stress, there is absolutely zero plastic strain. So the plastic strain only starts when the stress goes beyond your yield stress value. So before that, the stress simply increases vertically in the stress versus plastic strain diagram, because the entire strain is only elastic strain. So this simply goes vertically. The stress strain diagram, stress versus plastic strain diagram, simply goes vertical, and after that it follows a curve. And as we discussed, hardness is resistance to plastic deformation, which basically means d sigma d epsilon p, differential plastic strain, is d sigma divided by h. What is h? H is the hardness or the resistance to plastic deformation. Because stress versus plastic strain curve is a nonlinear curve, hence, that resistance is a function of plastic strain and must be defined for differential quantities. Now, what is that resistance? That resistance is essentially the slope or the tangent at any given point on the stress versus plastic strain diagram. So if you take any point on the stress versus plastic strain diagram and draw a tangent, the slope of that tangent is the hardness. Okay, and the slope of the stress strain diagram in the stress versus strain diagram, stress versus total strain diagram, that quantity is called the tangent modulus. This slope is called the tangent modulus. Okay, so this one, as you can see, it is much smaller than the slope in the elastic part, or that is the Young's modulus. So the tangent modulus is much smaller than the Young's modulus. So if I write the differential total strain, that is composed of differential elastic strain and differential plastic strain, this of course is d sigma divided by E, and this of course is d sigma divided by h, and this right here is d sigma divided by et. Now the numerator is same for all the three terms, so eventually you get the following expression for et, which is E times h divided by E plus h, which can be further modified to show that Et is Young's modulus 1 plus h divided by E. Sorry, I made a mistake. H divided by 1 plus h divided by E. Now H is the hardness, that is the resistance to plastic strain, is much smaller compared to resistance to elastic strain. And this only tells you that Et isn't just smaller than E, but it is many times smaller than E. And actually, because h by E is very close to 0, so this can be approximately equated to h. So imagine if h is approximately 1 in 200 of E. Of course, h is not a constant. Let's say the average value is around this. So Et would also be around 1 by 200 of E. And actually, Et would be smaller than both of these quantities. Sorry, it would be smaller than both of these quantities. Okay. Now, now all of this is more relevant to tensile test. Okay. For today's experiment, we need to know a little bit different definition for hardness. So this definition of hardness, that is resistance to plastic deformation, and this representation of hardness in the stress strain diagram is a general definition of hardness. Okay. Now, when we talk about hardness tests, we are talking about a very specific type of hardness, and that hardness is not uh, uh, resistance to. So there are two types of plastic deformations. So one is a bulk plastic deformation. There is the type of deformation that occur when, let's say, you are bending a rod. You're taking a rod and then you are bending into a U shape. Okay. Or maybe when you are forging uh, forging a rod into a different shape. Okay. When the entire object or a major part of the object is going through substantial amount of plastic strain or plastic deformation. Okay. When you are providing a substantial amount of plastic deformation to a given component, that sort of plastic deformation is bulk plastic deformation. And what we just learned is the definition of hardness that we just learned is the resistance to bulk plastic deformation. But for today's experiment, we are interested in learning about resistance to localized plastic deformation. Okay. I'll give you an example. Let's say you have this large disk. Okay. And in that, I take a sharp object, also known as the indenter. It can be, shaped like a nail or maybe a round edged, whatever that may be. And you make an indent with that indenter. Okay. So basically you apply a substantial amount of force in order to cause plastic deformation locally. So the major part of the component remains unaffected. The stress in the major part of the component, the deformation in the major part of the component will be, for most part, it would be very small, and even the for the immediate neighboring part, okay, that might be within the elastic limit, but except for except for the region very close to the indentation, where there would be substantial amount of stress, and so you understand, right? I'm just creating a hole using that indenter in the specimen. So I'm just creating an indentation. So so the so in that indentation and the region extreme just attached to that indentation, okay, there would be plastic deformation, substantial plastic deformation. But let's say, if you can think of this, imaginary boundary beyond which there is no plastic deformation, and if you are sufficiently away from the indentation, there you can the stresses and the strains that happen during the indentation process would be much small. Okay, so let's say the yield stress is 200 MPa. Okay, so obviously, if I consider the yield stress is 200 MPa, then let's say that at the time of indentation, in the region where the indentation is being created, at the indentation, at the or where you are indenting, there the stresses would be more than 200 MPa. Now, if we're slightly far away from that region, let's say this imaginary circle right here, if you're beyond this circle, or but still very close to the indentation, you might experience stresses of the order of 20 or 30 MPa, well within the elastic limit. But if you are far away from the region of indentation, the stresses are, let's say, less than 1 or 2 MPa. Okay, so this is the type of plastic deformation that you are talking about. Okay, so and this is the type of hardness that we are talking about. So here we are looking for resistance to localized plastic deformation. So in our case, the hardness is resistance to localized plastic deformation. And in the Viva, if I ask you what is the definition of hardness in relation to our experiment, the statement is it is the resistance to localized plastic deformation. The example being an indentation or maybe a scratch. So instead of taking this sharp nail-like object, I can take a knife. I can imagine a knife edge, sharp knife edge, this one, okay, and try to make a scratch. So it's like zero dimension in plastic deformation. It is one dimensional plastic deformation. Okay, because you can make a line out of a scratch, right? So even a scratch is extremely localized. Okay, and so all of this can be classified into or generalized into localized plastic deformation. And I'm repeatedly mentioning this. For you, the definition of hardness is resistance to localized plastic deformation. The example being scratches and indentations. Okay. Now the question is, why? Why should we know about a property? Okay, so why should we know about the hardness, which is resistance to localized plastic deformation? Why do I need to know about this property? Think about this. Okay. You could be working with, on a day-to-day life, you could be working with a set of brittle materials and ductile materials. Okay. If you have a component made of ductile material, okay. Okay, first of all, what do the scratches and indentations do? So let's start with the scratch. Okay. So scratch, essentially, a surface scratch is essentially a crack A scratch is essentially a surface crack. So if I take a cross section of this scratch, it looks like a crack, a surface crack. And if you're working with a ductile material, it can respond to that crack in a given way, and the brittle material would respond to the presence of a crack in a different way altogether. Now, let's say if I load this component in presence of this surface crack, what happens? So I hope by now you know something called stress concentration. This happens. Be it a ductile material or a brittle material, this thing happens. Okay. So if I apply uniform stress to a component which has a surface crack, okay, that crack may or may not be generated due to a scratch by a sharp object. Okay. I'm talking about day-to-day application, like the screen of your cell phone. Let's say if you put keys and other sharp objects in your wallet along with your cell phone, and those sharp objects, one of those sharp objects would make a scratch on the screen of your cell phone. Okay. Now, how severe is that scratch? That we need to understand, and then we need to know how much is the resistance to, having that scratch. So can that scratch be severe? Let's look at it. So, so if you are really far from this region of the crack tip, okay, the stress is very nominal. So you applied uniform stress. So that uniform stress is more or less the stress state if you are very far away from the. So this much is, let's say, sigma. This, so very far away from the. So I'm choosing y-axis to represent the stress. This axis right here is essentially the x coordinate itself. So the stress is the nominal stress sigma if you are far away from the, or let's say sigma 0, far away from the crack tip. But as you are very close to the crack tip, the stress, ideally, if you use an elastic model, ideally it goes to infinity. And why is that? Okay, I'm not saying it ever goes to infinity, but ideally it should go to infinity, because no material can withstand an infinite amount of stress. Okay, so what happens essentially? So we'll look into what happens. Okay, but ideally it predicts that at the crack tip the stress becomes infinite. That's a theoretical prediction based on elastic assumption. Okay, but in reality, no material is truly elastic, and we classify those materials as we classify some materials as brittle materials. Those materials have very little plastic deformation, non-zero but very little plastic deformation, and the ductile materials are the ones which have substantial amount of plastic deformation. Now the materials, so the theoretical prediction is the stress goes infinite. What is the logic behind that? Mentally, you can think of dividing this geometry into segments that bear the equal amount of force. Now, if you are far away from the crack, those regions could be uniformly separated. These regions carry the same amount of force as the next or the previous one. Okay, so if you multiply the sigma 0 with the cross section, let's say A0, so the total force is A0 times sigma 0. Let's say I'm making those segments, okay, which basically carry, I'm just dividing into segments which basically carry equal parts of that force, sigma 0 A0. If I make 100 segments, so each of them carry 100 of that force. Now, if I keep on doing so, obviously in the region of the crack, there is not enough material available. So these regions, once you reach the closer to the crack tip, try to make certain curvature. Okay, and if you are, you know, a bit far from the crack tip, okay, this curvature diminishes, and if you're really far from the crack tip, this curvature essentially vanishes. Okay, so for the region where the curvature has vanished, the stress is the nominal stress. But if you zoom into closer to the crack tip, okay, this is what is happening. So all of these boundaries of those segments which carry the equal loads, they kind of have concentrated in the vicinity of the crack tip. Okay, I mean the next line would essentially pass through this. Now imagine if you are far from the crack tip, okay, this much region is carrying, let's say, 1, 2, 3, 4 parts of that 100th of A0 times sigma 0. And all of that has been concentrated near the crack tip into this tiny region. Okay. So because of that, the stress, the force per unit area, okay, kind of skyrockets at the crack tip. And that's the elastical, that is the theoretical prediction using the elastic model, assuming the material to be perfectly elastic. It is always, deforming elastically, but no material does. So even the ones we classify as brittle material have tiny bit of plastic deformation, extremely tiny, but there is some. Okay, and you'll be surprised to know even glass has some certain amount of plastic deformation. So so the point is, in real life, the material responds to this behavior in a slightly different way. The fact is, the stress doesn't go to infinity, but the stress, let's say this one is the crack tip, the stress still reaches a very high value. Now, if indeed the material is a ductile material, the one which is capable of having plastic deformation. Now see this value of stress concentration, of course. Okay, so this is like the sigma max, and the stress concentration factor is the sigma max to this nominal stress. It is always greater than 0. Now, this value of stress concentration depends on the sharpness of the crack, of course. The sharper the crack, the higher is the stress concentration. That means if you take a tinier sliver, if you take a more sharp object and make a tinier sliver of a crack, then the stress concentration would be even higher. Okay, and to this high stress concentration, okay, ductile and brittle material can respond in a different way. A ductile material can have substantial plastic deformation exactly at the crack tip. And if you have substantial plastic deformation at the crack tip, this is what happens to the crack. The crack becomes blunt due to substantial plastic deformation, because stress is highest over here. So obviously the plastic deformation is also higher over here. And because of that, there can be a blunting of the crack tip. I'm not saying because of that the ductile material can always prevent a crack propagation, but blunting essentially reduces the stress concentration factor, because the stress concentration factor K is dependent on the sharpness of the crack. This thing, however, is absent in a brittle material, practically absent, because brittle materials cannot have substantial plastic deformation. Once they develop, once there is a stress concentration, this crack once the stress value is certain stress, the maximum stress is certain value, okay, this crack starts propagating, okay, And what happens if the crack starts propagating for a brittle material? So what you have is a larger crack. So more area now is absent from bearing the load of the bearing the applied load, and this continues, and this so this becomes kind of perpetual and eventually leads to fracture of the specimen. And for extremely brittle materials such as glass, that's a severe condition. Okay, so the point is the scratching, the indentation, this localized plastic deformation. Okay, of course, bulk plastic deformation has its own set of problems, but you need to understand, to cause localized plastic deformation, you do not need a substantial amount of force. So as we were discussing, if you have sharp objects as keys in your wallet along with your cell phone, without having an external agent, just because of the simple interaction between the two, there could be a scratch produced on the exterior of the screen of the cell phone from the sharp object. Okay, so unlike the bulk plastic deformation, you don't need that gigantic amount of external load. So we need to give special importance to this type of hardness and this type of plastic deformation. Okay, so if indeed there is a scratch on a glass component, okay, that can indeed be severe. Okay, so you want to prevent a scratch or an indentation on a brittle material as far as possible, and therefore you want to improve on a certain property, and that property would be hardness. And hence it is worthwhile looking into the details of that property, that is hardness, or how do we measure hardness. So now we'll be talking about different methods of measuring hardness. এই অবধি সবকিছু বোঝা যাচ্ছে?
হ্যাঁ স্যার।
আচ্ছা, একটা জিনিস বলি, আমি জানি না তোমরা নোটস এটসেট্রা নিচ্ছ কিনা। একটা জিনিস বলি, আমি বোধহয় আগের সেমিস্টারেও বলেছিলাম ডিটারের বইটা দেখতে বলেছিলাম কি?
হ্যাঁ
হ্যাঁ স্যার।
ওই বইটা পিডিএফ ফরম্যাটে হলেও জোগাড় করো। ওকে, and that has a dedicated chapter on hardness test. Of course, if you have gone through the book, then you know that there are dedicated chapters for all the experiments that you did: tensile test, torsion test, impact test, and you will also have a dedicated chapter for hardness test. So একটা ক্লাসরুমে আমি হয়তো একটা লিমিটেড অ্যামাউন্ট অফ জিনিসই বলতে পারি, হয়তো কিছু মিসও করে যেতে পারি, ভুলে যেতেই পারি বলতে গিয়ে। তো মাই সাজেশন উড বি ইউ শুড গো থ্রু দ্যাট বুক। ওকে, ফর অথবা আমি বললাম হয়তো তুমি লিখতে ভুলে গেলে বা খেয়াল করলে না শোনার সময়। সো মাই সাজেশন ইজ দ্যাট বুক ইজ supplementary to whatever we are discussing here. Okay, so definitely go through that book. Acha, measurement of hardness. So there are three different types of hardness tests. One is different types of hardness tests. On the basis of how the hardness is tested, there are three types of hardness tests. Okay, so one is of course indentation based. The other one is scratch based. The third one is rebound test. Now you understand what are indentation and scratch tests. Okay, and for indentation test, actually today we will be doing two experiments which are kind of indentation tests. Okay, now this rebound test is something that needs to be explained, because we can understand what are these two tests. So in one you do an indentation, and in the second you take a knife like sharp object and make a scratch. What is the rebound test? So imagine this is your specimen made of a given material, which has been placed on an anvil. So what you do is you let your indenter, so this is your indenter, either free fall or maybe powered by some pneumatic source, that is, let's say, air pressure. It is powered with air pressure, and you let it collide with the surface of the specimen, okay, or make an impact on the surface of the specimen, and then it would bounce back. Now after bouncing back, you note down, once it rebounds, you note down the rebound height, okay, or HR. You note down the HR, and that HR is actually your measure of hardness. Okay. Now, can you tell me, if I were to plot hardness is typically represented as hardness number, and if I were to plot the hardness versus rebound height, okay, should the curve be increasing or should the curve be decreasing? You'll have to go back to the definition of hardness. Hardness is resistance to plastic deformation. Okay. Now imagine if the indenter has perfectly elastic collision, it would bounce back to the maximum height.
Decreasing, sir.
Okay. Yes. And if it, uses some of its kinetic energy to create an indentation, which is essentially a plastic deformation, then it would bounce back to a smaller height. And more energy it spends in creating indentation, it would bounce back to smaller height. So the relationship is not direct, but an inverse relation, which basically says that if the indentation height, the rebound height is higher, that means the hardness is sorry. The relation should be direct, right? What I mean by that is, if it spends lesser amount of energy in creating the indentation, which basically means it couldn't produce that much of plastic deformation, okay, that means the resistance to plastic deformation is higher. Therefore, if the rebound height is higher, it means the hardness is higher. If it is, the perfectly hard body where there is only elastic collision, then it would bounce back to maximum height. So it's a direct relation, hardness number and rebound height. Okay, so that's the idea behind the rebound test. Now, at this point, I would also like to mention something called Mohs scale. So in early 1900s, so early 20th century, there were not as many methods of testing hardness of a material as we have now. Okay. And one more thing, just like in isotope impact test or Charpy test that we didn't do, the measured value, let's say the IZ number, okay, only makes sense when you compare two materials. Okay, so an IZ number is not equivalent of yield stress, because if I am given the yield stress, then I can use a factor of safety, knowing that if it is a ductile material, I will take it to be somewhere around 2 to 5. and then I can get a stress, maximum stress that I can allow my component to have, and then I can have a working stress and maximum stress in my structure. Let's say I'm designing a cantilever beam with a end load cantilever beam with an I section with an end load. Okay, so then I can choose the dimensions so that the maximum stress in my system is smaller than this working stress, which is yield stress divided by factor of safety, and I can choose that factor of safety to be somewhere around 3, let's say. Okay, so the point I'm trying to make here is yield stress, which marks the initiation of plastic strain. If I have that value from an experiment, let's say tensile test, then I can use that value directly in a designing operation. In a designing job, I can directly use that value. Such is not the case with Iser number. The value of the toughness that you get from Iser number, if we consider that Iser number is a true measure of toughness, that we cannot comprehend unless, of course, we compare two materials. So even in Iser test, we tested on two different materials. One was aluminum and the other one was brass. Today also, for each of the experiment that you do, we will be doing Rockwell Hardness Test and Brunel Hardness Test. For each case, we will be taking specimens of two different materials. So the hardness only makes sense when you compare two different materials. Does that mean hardness doesn't have a unit? Yes, hardness has a unit. Just like Iser number had a unit, which was the unit of energy in British system or APS system, which was foot-pound. Okay. For example, yield stress would be in megapascal. Okay. But even with unit, you cannot make sense of a given Iser number unless you compare the value with a certain other materials, more than one maybe, or maybe at least one other material. Then you can make a comparison that one material is tougher than the other. Same thing applies to hardness. So even in hardness, only when you compare the hardness numbers of more than one material, then you can make a sense that one material is harder than the other. Okay. Now, if you do not conduct any of these hardness tests based on indentation or anything, the simplest test that you can do is you can take two materials, material A and B, make sharp objects out of those two materials, and try to make a scratch using one of them. So using one of them, try to make a scratch on the other. Okay, and whichever material is able to make a scratch on the other material, that material is the harder material. Okay, so in this way you can rank the material. Okay, instead of actually evaluating the hardness number that today we would be doing, in early 1900, okay, this is the name of the scientist who prepared that scale, okay, with 10 different materials. So he ranked 10 different materials according to their hardness, and the basis for that was he would make sharp objects about any two materials in this list and try to make a scratch with one material on the other one. Okay, and whichever material is able to make a scratch goes to the higher rank. Okay, and whichever material is not able to make a scratch goes to a lower rank, and this way the ranking is done. Okay, now this was early 1900. Can you guess what material must have topped the chart?
Iron.
The diamond.
Diamond. Okay, and the 10th material was talc, which is a mineral. Okay, so which is a very soft material. The opposite of hard is soft. So this is your first assignment. So go search in the internet and write a short note and the complete list of Mohs scale. ওকে, এই অবধি বোঝা গেছে?
Yes, sir.
Okay. Now let's discuss the two experiments that we will be doing today. আচ্ছা, একটু আগে আমি বললাম that hardness has a unit. Okay, এই স্টেটমেন্টটা, the statement makes more sense when we talk about Brunel test. Okay, so let's first discuss Brunel test. So it's an indentation based test. Okay, now an indentation based test could be of two types. So the idea is same. You place a specimen on the anvil. Okay, you take an indenter, which in case of Brunel test is the sphere. Okay, you would apply a force F, and because of the applied force F, the indenter would create an indentation whose depth, let's say, is T. Okay, now there are two different types of indentation tests. In the first case, F is a constant, and we get an idea of the hardness from this depth of indentation. Okay, so today in both the experiment, this is the case. The force is a constant, and we get the value of the hardness number from the depth. So whichever material is harder material will have a smaller depth of indentation, and whichever material has larger depth of penetration is obviously the softer material. Okay, number two is in which T is a constant. So you want to create a given amount of indentation, and you would apply as much force required. So you'll be adjusting the force. You'll be providing more and more force, just the right amount to required, just the right amount required to cause the given depth of indentation. Okay. Now here we are, working with only the first variant. Okay, and that F value for Brunel test is 3000 kg force. Okay, that is approximately 30 kilonewton. Okay, 1 kg force is 10 newton or 9.81 newton. So you can do the math. Okay, and this indenter is 10 millimeter diameter, and this part is important. Hardened steel ball. During the Viva, I can bet 50% of you would give me this answer. What is the indenter for Brunel test? 10 millimeter steel ball. And that's an incomplete answer. The fact is that term right there, hardened, I don't know what is the method that is used to harden the steel ball. Was it by forging? That is, was it by work hardening? Was it by nitrogen or hydrogen atom were penetrated into the into making a interstitial solution? I don't care. but the ball is the indenter is supposed to be, an indenter is supposed to be much more harder, okay, compared to the specimen, the material of the specimen that you are testing. Otherwise, what would happen? Because of the force that you are applying, the indenter would deform along with the specimen, and you are measuring the indentation by the movement, downward movement of the indenter. And if due to the applied force, the indenter also compresses plastically, so that compression is also accounted as the depth of penetration or depth of indentation, and that just gives us wrong measurement of the depth of penetration, and therefore we get wrong measurement of the hardness. So the indenter must not be deforming not beyond elastic limit, and even elastic limit, of course, it must deform only slightly. So this needs to be hardened. Okay. Why the hardened part is important? Again, because one of the specimens is made of steel. So you'd be taking specimens made of steel, mild steel, and then there is brass. Okay. And if you just say that the indenter is steel ball, then that doesn't make sense. You need to mention that it has been specially treated to which can be used for testing a mild steel specimen. Okay. In Brunel test, the hardness value is called the Brunel hardness number. Okay. And this Brunel hardness number is essentially this force right here divided by the area of the indentation. Now, what is the area of indentation? You see, imagine this is the specimen. And after indentation, once the indenter is removed, okay, so this, there is a dent, right? There is an indentation, and that indentation, that area, the surface area of that entire indentation is this A indentation. Now, how do you get that area?
ইন্টিগ্রেশন করে বের করতে হবে।
হ্যাঁ। So imagine this is the indenter, and this much is the depth of indentation. This is the center, and this capital D right here is the diameter of the indenter. Okay. And you will have to figure out this area. So you see this circular arc, that is not semicircle, of course, or quarter circle, okay, because the center lies above. So this part, imagine that is revolved around this axis right here. Okay, so that area we are talking about, this area right here, this crater right here. So, of course, we can use Papa's theorem, but I'll not complicate it in that way. Let's say this angle is theta, and this much is d theta. So this differential length would be d by 2 d theta. And if you revolve this d by 2 d theta, okay, Achha, by the way, this distance from the axis is d by 2 sine theta. Okay. Now, if you revolve the small segment, if you revolve it about this axis, so the differential area is twice pi d by 2 sine theta, twice pi d by 2 sine theta times this differential length d by 2 d theta. Okay. So this area of indentation is this much, integration twice pi or pi d squared by 2 sine theta d theta. And this goes from 0 to up to this value, right? Up to this point. But how do I denote this angle? So you see, this is a circle, or this is the, indenter, and let's say this much is the depth of indentation. Okay. So if I draw a parallel line, so this much is d by 2 minus t. And if this angle is theta m, the maximum theta, so cos theta m is d by 2 minus t, because d by 2 is the radius, minus t divided by the abscissa, which is d by 2. Okay. So here the limits are 0 to cos inverse d by 2 minus t divided by d by 2. Now, if I integrate sine theta, I get minus cos theta. Okay. So cos 0 minus cos of cos inverse this quantity, which is simply this. Now cos of 0 is 1. So I have pi d squared by 2. So in the end, I have this A indentation is pi d squared divided by 2 times d by 2 minus d by 2 plus t divided by d by 2. So these two cancel out. This is the depth of indentation t, and these two 2's cancel out. So in the end I have pi capital D times t. So Brunel hardness number is F divided by pi d, that is the diameter of the indenter, which is 10 millimeters, times t, the depth of indentation. Okay. Now the diameter of the indentation, if I call that small d, so this small d, as we discussed, this small d is this quantity. This thing is small d divided by 2. And small d divided by 2 is square root of capital D divided by 2 whole squared, that is this thing, minus capital D divided by 2 minus t whole squared. So that would give me small d divided by 2. Okay. So by measuring this small d also, so the thing is, when actually measuring the depth of indentation, there is no way to directly measure the depth of indentation. So what we do is we measure this small d, and from the measurement of the small d, we can figure out how much is the depth of indentation using this formula. So if I can show you, let's say this is the center of the indenter. This is the radius of the indenter, which is capital D divided by 2. And this much is, let's say, the depth of indentation. So length of this side should be capital D by 2 minus t. And this side is small d by 2. Okay. So this basically represents, this small d is the diameter of the indentation. Imagine this is that segment of the indentation. Okay. Okay. So, so what we learned from this is, first of all, the Brunel hardness number is force divided by some area pi dt. First of all, what we learned was that Brunel hardness number is inversely proportional to the depth of indentation. You see this AF and capital D, these are constants. These are the specifications of the experiment. AF and D are constants. The other thing that we know, that this Brunel hardness number has the same dimension as stress or modulus such as Young's modulus, because it is force per unit area, right? So it would have units such as MPa or GPa. Okay. And actually, hardness can be thought of a material property, or it can be thought of a modulus. So in reality, we earlier talked about bulk plastic deformation. So even in bulk plastic deformation, okay, we talked about tangent modulus and Young's modulus in these two regions. And as we showed, that tangent modulus is approximately the hardness. Okay. So his hardness is also a modulus where you are comparing resistance to, so where you are talking about resistance to plastic strain. So when you plot stress versus plastic strain, you have hardness as the modulus. So here also you see it turns out to be having the same dimension as modulus. You see this pi is unitless. This one can be thought in millimeter. This one could be in millimeter. And if this thing is in Newton, then you have BHN in megapascal. Okay. And if you adjust for decimal places, you can also get it in gigapascal. Okay. So typically hardness values are of the order of gigapascal, the same order of magnitude that the different other moduli have. Young's modulus, shear modulus, different other moduli have the same order of magnitude, that is gigapascal. So hardness in a sense is a modulus. Okay. As we discussed earlier, it is resistance to localized plastic deformation. Okay. And this diagram right here, don't confuse with this one. This is simply a comparison with the bulk plastic deformation. Now this relation is important, the inverse relation, the relation with of hardness number with the depth of indentation is not universal for all the experiments. So in Rockwell test, that relation is in Rockwell test, it is called Rockwell hardness number. Okay, but RH stands for Rockwell hardness. In Rockwell test, there are different scales. For example, if we take B scale, then we have HRB. So that would be C0 minus C1 times T. Okay, so there is a kind of a linear relationship. So instead of a inverse relationship, here the relationship is linear. But in both cases, you would see if the depth of indentation increases, hardness number decreases. If the depth of indentation reduces, the hardness number increases. Okay, so if you are testing on two different materials, the one with the lower depth of indentation is the harder material in both cases. But here the relationship is linear, and probably the reason for Rockwell test to have multiple scales. Okay, so Rockwell test have many scales, probably G or H. Okay, and that is your second assignment. Go over the internet and write a short note on different scales, their purpose. There is a purpose of having multiple scales, and their specification of each scale, of Rockwell test. Now these scales are meant for materials of different hardness ranges. So if I take scale A, that can measure hardness for a given set of materials. Okay. For our experiment, Rockwell B scale would be used. That is the most suitable scale. So you can, put different, you can group different type of materials for a given scale. Okay. So a given scale is suitable for only a given set of materials. If the hardness range of the materials is much higher or much lower, probably you need to switch for a different scale. So in any scale, the Rockwell hardness number varies between 0 to 130. But if you are less than 30 or more than 100, you should probably switch to the neighboring scale, neighboring lower or the higher scale. As long as the values are within 30 to 100, you are good to go. But if the hardness number is lower or smaller than this range, you should probably switch to a different scale. That's the idea. Now, each scale has different specification. So what vary? Both the quantities vary, the load and the indenter. Of course, even in Rockwell test, the force is a constant. If once you choose a given scale, the force is a constant. For example, if you choose B scale, this much is 100 kg force. And the indenter is 1/16" hardened steel ball. Okay. But if you go for C scale, this load is 150 kg force and the indenter is diamond braid. Okay. So simply by looking at the specification, you know that which of these scales is meant for hardened material. Okay. So I'm just giving you the example of two scales, but as many you find over the internet. I need you to list all the different scales, the specifications, all the different scales, and you should also explain what is the purpose of having multiple scale in Rockwell test. In addition to having multiple scales, Rockwell test has something called a minor load. Oh, already attendance 12-তে চলে গেছে, মানে এক্সপেরিমেন্টটা তো শুরুও হয়নি এখন। খুব ভালো। Minor load, which for both B and C scale is 10 kg force. So this is your third question. What is the purpose of a minor load in Rockwell test? Okay, so that you try to answer. But before that, notice one thing. Between Brunel test and Rockwell test, F has changed from 3000 kg force to 100 kg force, and diameter of the indenter has changed from 10 millimeter to 1/16". Now, how much is 1/16"? That is 25.4 divided by 16 millimeter. Now, 25.4 is very close to 25.6, and 256 is actually square of 16. So this is approximately 1.6 millimeters. Okay, which is about 1/6 which is about 1/6 of 10 millimeter. Okay. Now, if this is the diameter of the indenter, if we now compare the area of indentation, this ratio for that one would be square of that, which would be somewhere between 36 to 40. Okay. Actually, 1 by 6 square or 6 square is 1 by 36, but this is also not exactly 1 by 6. So you see, the area of indentation in case of Brunel test is around 36 to 40 times higher. And that's why the applied force is also 30 times higher. Okay. That is one thing to notice. And let's now talk about the importance of a minor load, or what is a minor load.
স্যার
Yes.
স্যার রকওয়েলের ক্ষেত্রে তো যেমন ব্রিনেলের ক্ষেত্রে আমরা এরিয়া অফ ওই আইডেন্টার এরিয়াটা নিয়েছিলাম, রকওয়েলের ক্ষেত্রে তো ডেপথটা নিতে হয় আমাদের, তাই তো?
না, আমরা যখন রকওয়েল টেস্ট করব তখন আমরা the instrument would directly give us the Rockwell hardness number. I mean, otherwise যেটা হতে পারতো যে we would be given the depth of indentation, okay, and from the constant, so HRB C0 is basically 130. If there is no indentation, then the Rockwell hardness number is 130. So this thing minus this C1 times T, C0 minus C1 times T. So this C1, I believe for our instrument, that is 0.002. So if you have, where this T is basically in, I don't know what it is measured in. Is it 0.002 or I need to check whether it is 0.0022 or 1 by 0.002 or something. So basically, that constant would be given to you. I'll share all the laboratory instruction sheets, so you'll find that in that document. So, this C1 is provided to you. From that, you could have gotten the hardness number. But our instrument is such that you directly get the hardness number, and later you would be asked to find out the depth of indentation from the same constant. So the depth of indentation would be T is 130 minus HRB times C2, where C2 is 1 by C1, and possibly this C2 is 0.002. So let's say if you get a hardness number of 70, so T would be 60 into 0.002, that is 0.12 millimeter or something. Okay. So that's the idea. We directly get the hardness number, we have to calculate the depth of indentation. So next thing is purpose of a minor load. So one thing to notice that the indenter in Rockwell test is substantially smaller than that of in Brunel test, and there is some advantages to that. You can do multiple indentation, okay, on a given area, but there are certain problems associated with that. So one of them being that imagine this one is your specimen, okay, and let's say it has some subsurface flaw, okay, let's say blowhole or something, okay. So at the time of manufacturing, it develops some subsurface flaw, and you are placing your indenter right here, okay, and applying the force. So applying the F, which is for Rockwell test, which is known as the major load. The total load F is called the major load. Okay. So if you are directly applying the major load, what will happen? If indeed there is a subsurface flaw, such as this blowhole right here, okay, so this blowhole will collapse, and that depth of the blowhole is also added in your measurement of depth of indentation. and that is an incorrect measurement. So this is how the Rockwell test proceeds. So first, you apply F minor. What does it do? It collapses any subsurface flaw and causes a little bit of elastic deformation of the specimen. Okay. Then you need to apply F major. And what does F major do? F major, so when you applied F minor, it collapses any subsurface flaw and sits on a given level, and that level you now describe as the datum. And that level is now the level beyond which you make any measurement. So the next thing that you do is you apply major load, and the indenter, even proceeds further into the material, and therefore creating both elastic and plastic deformation of the specimen. Okay, more elastic and more plastic and more elastic deformation, plastic deformation and more elastic deformation. Now the next thing that you do is you remove the major load where the minor load is still there. Okay. So what would happen? The specimen would slightly move upward, only slightly, only to recover the part of the deformation that is elastic. Major part of the deformation is plastic, which would not be recovered. So once it has slightly recovered, at that stage, you measure the depth of indentation. Where do you measure it from? You measure it from the datum. Okay. So you applied minor load, it sits on a level, that is the datum. You apply major load, causes more elastic deformation and substantial amount of plastic deformation. Okay, and then you remove the major load, minor load is still there. At that situation, your specimen regains some of its deformation in the form of elastic strain, but that is only very tiny component. But it is at this stage that you measure the depth of indentation. Okay. Where do you measure it from? From the datum height. Okay. So you take it from there. So this is how the force is applied with time. So you gradually apply F minor. You let it set. Then you apply F major. You let it set. Then you remove F major. Okay. You let it set and make measurement. And once the measurement of the indentation is done, then you remove the minor load. Okay. So this is all I had to say about the experiment. If you have any question, let me know. Otherwise, we can proceed for the experiment.
স্যার গ্রাফটা একটু দেখাবেন?
তোমার চিন্তা নেই, এই ভিডিওটা আমি শেয়ার করে দেবো।
ওকে স্যার।
আচ্ছা, so now we'll proceed for experiment video. ওকে, আমি আমার পার্ট এখন মিউট করে দিচ্ছি, তোমরা এই ভিডিওটা দেখো। ওকে, এই ভিডিওটা হয়ে গেলে তারপর আমরা আবার ডিসকাস করব।
Different type of material testing. Along with that, some other properties of materials also we also test here. The particular test which I am going to discuss
স্যারের আওয়াজ শোনা
is
যাচ্ছে?
related to hardness
হ্যাঁ,
of
স্যার।
material. What is meant by hardness of a material, that is basically discussed in the theoretical class. But before I start this particular experiment, which is Rockwell hardness test, I must also try to recapitulate little bit of what we are supposed to discuss in the class here as well. The thing is, we are going to do some test related to hardness. So we must know, rather we must recapitulate what is meant by hardness. It's basically the resistance to localized plastic deformation. It's resistance to, we can call it resistance to scratching, we can call it resistance to cutting, resistance to abrasion. So in number of different ways, we can describe the property of hardness. But as far as hardness measurement is concerned, there are different techniques by which we can measure hardness of a material. This is a test which we are going to do maybe within the next few minutes. This is basically Rockwell hardness test, and this is a macro hardness test. We call it a macro hardness test. Similarly, we will also go for another test which is Brunel hardness test. I will show you what are the different aspects of a Brunel hardness test, what are the differences between Rockwell hardness test and Brunel hardness test. All these things will be discussed. Along with that, there are other tests as well, but all these tests, be it Rockwell, be it Brunel, be it Vickers, all these tests are generally known as the macro hardness tests. What is meant by macro hardness test? We are using a comparatively higher amount of load. Where from the concept of load is coming? Because I have already mentioned that it is basically resistance to penetration, resistance to localized plastic deformation. If it is so, I must give some load that will cause that localized plastic deformation. I am talking about that load. Now this particular load, if the load is in excess of more than 1 kg, 2 kg, 5 kg, 10 kg, or maybe 100 kg, or maybe 1000 kg, we often call those experiments where this amount of load is applied, we call them as macro hardness test. Another thing which we should keep in mind, that is, while doing any such test, we are trying to develop a penetration, an impression on a surface. This is one material on which we are going to do a testing. This material, as you can see, that this is a smooth surface, a polished one. On this particular material, we are going to create an impression. Now, we must measure how much big is the impression, or how much is the depth of that particular impression. In terms of that, we will be able to find out this particular material, whether it is very hard or less hard, or this is very, very soft. How? If the penetration or the depth of penetration which is created on this particular material is not that much, then definitely I must conclude that the material is hard. If the penetration or the depth of penetration is really big, really high, then definitely the material is not so hard. So we can try to understand the hardness of a material in terms of the penetration or the depth of penetration on this particular material. Okay, so this is one material. This is basically a mild steel material. We'll do a testing here in this Rockwell hardness test. We also have a material which is basically brass, on this surface also. In fact, we can, if you magnify it, you can find out some of the indents are also there, some of the indentations are already there. Okay, so this type of indentation we are going to create. But before I start the experiment, I want to show you one thing. If you focus on this particular thing, you will see that a lot of small points are observed from a distance also. Okay, if you want to find out how much is the dimension, how much is the radius of this thing, it may be less than a millimeter, but it is never like 1 micron. It is never like 1 nanometer. Why I am saying like that? I have already mentioned this particular test is a macro hardness test. The type of penetration, the type of impression we are getting, the dimension of the impression is small, but small doesn't mean that it is of the order of micron or order of nanometer. If I go for a micro hardness tester, if I go for a nano hardness tester, I will come across that type of thing. So now let us come and try to do this particular experiment here on the Rockwell hardness testing machine. Before we start the experiment, let us explain one or two small things. This particular machine is an old one. You can see that this is an old one, and this particular machine, it has number of scales written over here, number of scales. Maybe probably from distance you will not be able to find out very clearly, but you can try to find out that what are the different scales. Okay, so number of scales are there. Now these particular scales are required. Why? We can have different types of materials which are going to be tested. If I go for aluminium to be tested, if I go for steel to be tested, if I go for brass to be tested, we can need different type of scale. What is meant by a scale? Scale means on the dial, you can see that there is a dial. There are different types of reading we can get from this particular dial. If I know which scale I am going to use, accordingly I can read from here. Okay, there are number of scales already written over here. You can consult any standard book to find out what are the different possible scales. Each scale corresponds to one particular set of things. What is that? Each scale corresponds to, first, it is basically a particular type of indenter. Indenter, that particular material which is very hard, which is going to create the impression, that particular material is the indenter material. So we are supposed to have a particular indenter for a particular scale. At the same time, we must have a specific load which is to be applied on that particular material. Say, for B scale, I am talking about B scale. If I go for the B scale, we are going to use a hardened steel ball. Its dimension is very small, 1 by 16th inch. 1 by 16th inch only is the diameter. So this is a very small hardened steel ball. Hardened steel ball means it is already hardened, maybe by carbonizing, by nitriding, by cyaniding, or by some other method. It is already a hard ball. That is the penetrator. Okay. Along with that, we should also remember we are going to use a load. Going to put a load. How much is the load? 100 kg of load. We cannot see anything here which is 100 kg. If we go on the back side of the machine, we will be able to find out that there is some hanging weight. We are putting a hanging weight on that side so that the effect is coming on the front side, and this is basically, I am putting my finger at the tip of that penetrator. Here you can feel that there is a hardened steel ball. So we are putting the load from behind. We have a lever arrangement here so that the load comes here, and this particular penetrator, if I put the sample here, we can raise the sample, bring it in position, and then we can apply by a typical mechanism. We will show by a typical method we can apply the 100 kg load on this particular material, and that will create some impressions, very small impression. You can see very small impressions like this. Now, once this impression is done, it is our responsibility to find out how much is the depth of penetration. Because if the material is not so hard, then the depth of penetration will be big. If the material is hard, the depth of penetration will be small. But the machine has a beauty. What is that? It's true that we can find out. We have a sheet. Using that particular laboratory sheet, we can find out that how much. There is a provision in the sheet as well. I am not showing right now. You will be able to see it later. There is a provision in the sheet where you will have to write how much is the depth of penetration for each and every penetration, each and every test. You will have to find out how much is the depth of penetration. How we can find it out? It's a very small thing. How can we find it out? Find out the depth of penetration. The machine itself gives us a simple technique. There is a simple calibration and other thing by which I can find out how much actually is the depth of penetration. So machine, the dial will give me a data. The dial will give me a numerical data, and from that numerical data, using a particular formula, using a particular concept, we can find out how much is the depth of penetration. Definitely, if I use two different materials, one mild steel and one brass, definitely their hardness will not be same. If I assume that the hardness of steel is going to be high, that means the penetration, the depth of penetration here will be small. If this one is not so hard, little bit softer than this one, then definitely the penetration in this case will be high. So here in the sheet, if I write the actual depth in penetration, definitely I should get a clear idea. The particular case where the depth of penetration is more, definitely the hardness is less. The case where depth of penetration is less, definitely the hardness is more. So we can get a clear idea about the relationship between the depth of penetration and the hardness of the material. So this is what we are going to do. Before I start this particular experiment, I have nothing more to add, but once we finish, we will again add few things. Let us now go for the experiment. Okay, so now let us do the experiment. You see, he is putting the sample on the anvil. We call it anvil, on which the sample is being put. And now by rotating this particular thing, he is raising the sample. so that it comes in contact with the indenter. Probably you can see the indenter there. So the sample is coming in contact with the indenter, and there is a particular indication where the sample is properly gripped or not. Whether the sample is properly gripped or not. We can check that whether the sample is properly gripped by putting this particular, by focusing on this particular dial. Focusing on the particular dial, okay? Now let us fix it to 0. We are fixing it to 0.
black pointer 0 করে নিই পয়েন্টারে মিলিয়ে নিই ছোট কাটাটা ছোট ছোট পয়েন্টে আছে এই বড়
আসার কথা আসেনি কেন কাট
There are 2 pointers in the dial, you can see. We are raising that particular sample. The sample is coming in contact with that particular indenter, and you can see both the pointers, they are rotating, and the small pointer is just on that particular small black point. That shows that yes, we have gripped the sample properly. That means we have given a 10 kg, roughly 10 kg load, which is known as the minor load. So in this particular B scale where we are doing the testing, we need a 10 kg minor load for holding the sample in position, gripping the sample properly. That is already done. Now he will give the major load, which is 100 kg. He is giving the major load like this. You can see the pointer is moving. The pointer is moving. Gradually the load is being applied. So inside the material, inside the particular material which we are testing, there is some deformation, localized plastic deformation, it's taking place. It is basically plastic plus elastic combined. And now, after giving a 15-second time roughly, we can rotate one handle forward. Yes, please focus on this. Here you can see the value. Please read the value. How much is the value?
77.
77. So this is Rockwell B scale. 77 is the value. So we can say the Rockwell hardness number of this particular sample is 77. More correctly, it is RB77. That means Rockwell, R stands for Rockwell, B means B scale, and 77 is the value. So this is one value. Let us repeat. Let us get 2 other values. We will make an average.
Next.
Again you see, we are focusing on the pointer. It is coming to that black dot. Now he is setting the 0 mark. He is setting the 0 mark, and then he will apply the force, the 100 kg force. It will be applied gradually. It will be applied gradually. And you can see that it's rotating. The pointer is also showing some rotation. It will keep on rotating as long as the load is being applied. We will give a roughly 15-second time, and then we will try to get the exact data, the data from the machine. Okay, let us go for the data. How much it is?
78.
78. The initial, the first one was 77. This one is 78. One more, please, on the same material. But one thing is to be ensured that you see, before putting the next indentation, what he is doing, he is just shifting the position so that the first indentation is not being acted upon by another indentation on that. No, we should go for separate places for separate indentation. He is doing the same thing, repeating the same thing, setting the small pointer, setting the 0 mark, and then putting the actual load, 100 kg load. You see the pointer is rotating. At some point it will stop. And then giving 15-second time, we will go for the reading. Roughly 15-second time, because some amount of time is needed for the load to be applied completely, and also for the plastic deformation to take place. Yes, please. Yes, how much is the reading, please? Note down how much is the reading.
78.
78. So we are getting three different values, 77, 78, 78. We can take the average of this. Now let us go for the other material. The same method, the other material. This time it is brass. He is again putting the sample there. The method is exactly the same. Let him do the steps. He is raising it. He is raising it by rotating this particular one. Raising the anvil. The small pointer is coming close to that small point, black point. He is setting 0 mark, and now he will give the same type of load. Same type of load, major load, 100 kg. Done. Again you can see that dial gauge is rotating. It will rotate, and at some point it will come to standstill. We will again give roughly 10-15 seconds, and then we will try to get the reading. Whatever we are getting from this particular dial gauge is basically the Rockwell hardness number. I will definitely discuss few things on this later. Let us make the experiment first. Yes, please rotate it and get the value. Yes, how much is the value?
54.5.
Maybe 54.5, fine. 55. Okay, fine. We are just doing it 55, no problem. So here the hardness of Rockwell hardness number of brass is coming out to be 55. Let us take two more values quickly. Please ensure that it is not on a previous one. The indentation should be on a fresh surface. The same method you can see. Putting the 100 kg load, fine. The load is being applied. Gradually the load is being applied. Now the dial gauge, the pointer stops, and now he will rotate that particular handle to find out how much is the permanent value, permanent deformation value. So actually this is not the permanent deformation value. I will discuss that. How much is the value you are getting?
55.
55. So once again 55. Now the third step. Now the third step. Then we will discuss. Now the third step, and then we will discuss. The same step is being followed. The rotation of the dial gauge. As this particular material is a softer one, comparatively softer one, you can see that there is a longer time through which that rotation, the deformation is taking place, and definitely the amount of deformation is more. The depth of penetration is definitely more. We will check that later. It has stopped. Let us take 1 or 2 more seconds and then find out. Yes. Find out the value. How much is the value?
54.
54. So it's done. 55, 55, 54. So we can take an average of these three, and that is basically Rockwell hardness number. This is the particular data sheet which we have filled in here. Whatever data we have collected from this particular machine, that has been written here, and that already we have taken a photograph of this thing, and it will be shared with you. Okay, but what you are supposed to do, you are not just supposed to find out what are the values, not just supposed to write down the values or calculate. You are supposed to understand one more thing. What is that? I have already mentioned. In the sheet also you will find it, that inside the sheet there is something known as actual depth of penetration. we should try to find out how much is the actual depth of penetration in the two different cases. And we should try to correlate that in case of mild steel, the amount of actual depth of penetration, and in case of brass, the amount of actual depth of penetration, whether which one is bigger, which one is smaller, etc. We should try to find it out. Apart from that, we want to mention one more thing. What is that? Let us show you. Already I have mentioned that the penetrator which is being used for this particular testing, which has already been done, the penetrator has been used as the 1/16 inch dia hardened steel ball. But in my hand I am holding another penetrator. You can see it. This is having a very shining edge at the tip. This is known as a diamond braid. This is basically, believe me, it's diamond. It's a diamond braid. Why we are using diamond? Because diamond, as we all know, is a very hard material. If the material which we are going to test, what we have tested already? We have tested mild steel. What we have tested? We have tested brass. But definitely someone can ask you, someone can ask me to test hardness of a material which is not like mild steel, maybe high carbon steel, maybe something else which are known to be hard material. In that case, we will use this type of a penetrator, not using this hardened steel ball. We use diamond penetrator. In that case, not only the penetrator will change, but the major load which I am applying, in the case which I have shown, it was basically 100 kg major load. If I go for this type of penetrator, I should go for 150 kg of major load. Okay, so the load will change, the penetrator will change. The combination of load and penetrator, it is basically denoting a new scale. So we can go for Rockwell hardness C scale. If we go for the experiment which is already done, it is on B scale. If we go for C scale, we'll have to change the penetrator. We'll have to replace this one, the hardened steel ball, with this particular diamond braid, and also the major load is to be changed. Whatever load we are applying from behind, that was 100 kg, we should add this one as well. This is a 50 kg weight, that is also to be put, so that a 150 kg weight acts. So we have provision for different type of scales, for different type of material. Before I end, just one small thing. Already, if you look carefully, that particular sheet which is there will be shared with you. If you see the sheet carefully, you will find that there is a particular dimension of this thing, thickness of this thing, the diameter of this thing, everything is there. It is also supposed to be very smooth. If it is not smooth, then the result can be erroneous. So it must be very smooth, that is one thing. It must be polished. We should not put any indentation on a previously existing indentation. So these are all precautions. At the same time, we should keep in mind that there should be a thickness like this. If I go for a very, very thin specimen, what will be the problem? If I give a load on top, the response will come from the anvil, not from the material. So there is a particular problem. If the sample is not this much thick, very, very thin, then what should we do in case of a very thin specimen? Someone can give definitely a very thin specimen. What can I do for that? We should go for superficial Rockwell hardness test. There is a particular type of test known as superficial Rockwell hardness test. Okay, that is not done here, but it is possible. We should keep in mind that inside the Rockwell hardness test, right now, though we don't have the provision to go for superficial Rockwell, there is a special type of Rockwell hardness test where we can go for superficial Rockwell hardness test. The last point I want to mention is in the report. In the report, on the back side of the report, you will find a particular column where Rockwell hardness number, whatever you have got from here, that particular Rockwell hardness number is to be converted to Brunel hardness number. There is a column for that. That means, what I want to emphasize on, that Rockwell hardness number, whatever may be the value, maybe 77, maybe 55, whatever it is, we can convert it suitably by using suitable formula, conversion formula that is given over lip. You can find it here in this particular sheet. You can find it how we can convert the Rockwell hardness number to Brunel hardness number. So this is what we are supposed to share in this particular experiment. That's all. Thank you. Hardness test is basically one of the major experiments which we do in this particular laboratory, in applied mechanics laboratory. Already we have done Rockwell hardness test, and now we are going for the Brunel hardness test. During the Rockwell hardness test, I tried to mention a few things. That Rockwell hardness test results, which is nothing but Rockwell hardness number of a material, can be converted to Brunel hardness number. But then why we should go for the Brunel hardness test at all? If we can convert it, if we can get it from the Rockwell hardness data, why we should know that we should try to do this thing as well? Because this particular experiment has some speciality which is not there in case of Rockwell. In case of Rockwell hardness number, in case of Rockwell hardness testing, the type of impression we got, the material on which we were getting the impression was very small, in the order of few millimeter. Here also, the order of magnitude is not very big, but at the same time I must say that in comparison with Rockwell hardness, here the impression is bigger. Why the impression is bigger? I am using the same material, why the impression will be bigger? It can definitely be bigger if I use a huge amount of, high amount of load. Here we are using 3000 kg of load. In Rockwell we use 100 kg of load, 150 kg of load. Here we use 3000 kg of load. So it's a huge amount of load we are giving. At the same time, the penetrator, the indenter which we are using in case of Rockwell hardness testing, I told that it is 1/16 inch hardened steel ball, or in few cases we use diamond braid. But here I am touching this particular machine. Here we have a particular thing. Probably if we come closer and closer, then probably you will be able to at least feel that there is a very small ball here, very small ball. But the dimension here, the diameter of this ball is much bigger than the diameter of the ball which is used in case of Rockwell hardness test. So there is a big difference. What is the difference? Let me summarize. One, the ball or the penetrator which we are using here, that is bigger in size. Second, the load which we are going to give here, that is also quite high. Not 100 kg or 150 kg. It's 3000 kg. So it's a big one. Okay. Now, what we will do? We will try to put the sample here on the anvil. Try to put the sample here. What type of sample? Similar type of sample which we were using in case of Rockwell hardness test. So similar type of sample, a thick one. A thick one, maybe 10 millimeter, 20 millimeter is the thickness. So that amount of thick sample will be put on the anvil. Definitely that particular anvil can be raised. It should come in contact with this particular indenter, and then using this particular handle, we will put that particular load so that the load creates an impression on that particular surface. Definitely, as the load is more, 3000 kg, as the penetrator is bigger, definitely the indentation, the impression will be bigger. Now, not from the dial itself. This particular dial is not of that kind. It's not like the Rockwell. From the dial we will not be able to find out how much is the penetration, how much is the impression created. What we can do from this particular thing, just to record how much is the load which is being acting on this particular sample. What we can do is, from this particular impression, whatever we are creating, we can take the sample and observe it under optical microscope with a particular magnification. If we see it under optical microscope, definitely we will be able to find out that how much is the impression. We can have a scale fitted with a microscope eyepiece. We can have a scale. If I use the scale, or we can have a grid as well, depending on the microscope we have. We can have a simple microscope by which we can find out how much is the dimension. Dimension means how much is the diameter. Now we have a ready chart. Can I have the chart with me? Ajay, the chart please. Chart. We have a ready chart. We will show you the details of the chart. In the chart, we have number of columns. We have the diameter mentioned in millimeter. We have the load. We can use 500 kg of load or 3000 kg of load. In this particular case, we are using 3000 kg of load. So if I can measure how much is the diameter, then according to the diameter, I will find out how much is the Brunel hardness number. So we can find out against the diameter how much is the Brunel hardness number of that particular sample. What we will do? Now we will do the test here, and in the test we will take again 2-3 different readings on the same material at 2-3 different positions, and then using an optical microscope we will try to find out how much is the diameter of those samples, how much is the diameter of those impressions, taking an average of that, and definitely find out using this particular chart. We will try to find out how much is the actual Brunel hardness number which we will get from here. Once we get the average diameter, Average diameter may be number of readings from different directions, average diameter, then that average diameter is to be put against the value of Brunel hardness number. We can find out this particular value of average diameter, how much is the Brunel hardness. You can see the anvil here. The anvil is now lowered. He is putting that particular sample on the anvil, and then raising it. Rotating it in a clockwise direction, raising it, so that a load acts. Now it is in such a position that we cannot take it out. So it is properly gripped. It's gripped tightly. Now he will give the load. He is giving this particular pressure here, and that is basically applying the load. Okay. You see, this particular dial shows that this is 3000 kg of load. Okay. Roughly 15-20 seconds it will be given, so that the deformation is complete, the localized plastic deformation on the material, that is complete. And then we will try to take it out. Please see how big is the impression. In fact, on the same material, you can see two types of impression. This is for Brunel, and these are the smaller impressions for Rockwell. So you can just have a apparent comparison between these two. This sort of data we will take. This is one. Second data he will take. We can take third one, and then we will measure using optical microscope. Let us take one more first. He is taking another data, another impression he is creating, not at the same position, little bit away from there. He is giving the pressure here. Maybe for 15-20 seconds the load is applied. 3000 kg of load that is being applied, and it is applied through that penetrator whose diameter is 10 millimeter. I forgot to mention the diameter of the penetrator here is 10 millimeter. Okay, fine. Please take it out. You can see the two big impressions. These two impressions are from Brunel. Okay. Now the next step is we will go for brass, and then we will check all the data under optical microscope. Let us go for brass. Yes, on brass already number of things are there. Number of impressions are already done on brass. We should try to avoid any impression should not be on the previous one. It should be away from the previous one. Okay, we should do that, and then we'll try to find out how much is the average diameter. Once we get it from the chart, we will be able to find out the value. The same method, he is raising the anvil, bringing in contact, putting the load. 3000 kg is the value. 3000 kg is the value. From the dial you can see 3000 kg is the load. It will be applied for 15-20 seconds, and then we will take it out. The impression will be clearly visible, I hope. Let us see. Yes, here is the impression. You can see that this is the impression created on brass. Another impression we will take, and then we will measure. The same way we are putting the load. Okay, 3000 kg of load. We are bringing it down and find out. You may wondering why some of the holes are made white. Actually, we have put chalk inside. Nothing. The exact reason is so that once we do something, then we can identify which one we have just done. If the previous things are done by chalk, filled in by chalk, then the new one can be easily understood which one is done afresh. That's why we have put chalk on the previous things. Okay, so this is what we have done. Now we will use the optical microscope to find out how much is the diameter of this thing, how much is the diameter of this thing. This is brass. So on this we'll be getting number of data, because for this we can measure the diameter in different directions. We can measure diameter maybe 2, 3, 4 times. We will take an average of that, and that particular average value is the representative value for brass. we will try to find out corresponding to that average diameter how much is the Brunel hardness number of brass. Let us try that. He is doing the thing. Please show. He is measuring it on steel, on mild steel. Already it has done, the impression was created on mild steel. He is measuring on that. He will tell us how much is the value, how much is the diameter. We will note it down.
54.
Diameter 54. He is saying 54 is the diameter. We should note it down. 54 in our laboratory sheet, experiment sheet. We should note down. Okay, he wants to get a more closer view. Using the microscope, he is getting the value. How much it is?
60.
60. It is for steel. 60. Okay, fine. For one. Go for the other one. So the value he is getting, it may be 60 or something, whatever he is saying. Actually, he is rotating the whole thing and finding the radius, diameter at different orientation, at different directions. Number of positions he is measuring, and the more or less value is 60. Okay, another one, it is another one.
6 point, should be 6 millimeter. 6.5.
So it is 6 millimeter and 6.5 millimeter, not 60. So 6 millimeter and 6.5 millimeter in two different cases for steel. What about brass? Millimeter, I don't think it's right. It's 10. Okay.
68.
68, definitely. Not 68, 6.8 I think. 6.8. For brass it is 6.8, one case. What about the other case? It's being cross-checked.
5.8 হবে কারণ আপনি 1 থেকে শুরু করেছেন 5.8
Not 6.8.
থেকে শুরু করে দিন 1 থেকে শুরু করেছেন
তো জিরোতে লাগাবো।
জিরোতে লাগাবেন
5.8.
So in both the cases 5.8 or one case 5.8?
এগুলো কম প্রতিটা কম
So you cross-check it. Cross-check it.
আরেকটা ব্রাশে আরেকটা দেখে নি তারপর
তারপরে দেখো।
5.8.
So 5.8 for brass. Okay, let us repeat it. There may be some mistake. Let us repeat it from steel, for steel. Please check. Let him check, let him check.
Five.
So 5 for one. Go for the next one.
Five point
5.1. Okay, fine. So we are getting the values, we are getting the impressions, and we are measuring the impression, and the diameter is coming out to be, in case of steel, it is roughly 5.1, something like that. We can take an average. In case of brass, it was coming out to be how much, Ajay? In case of brass, it's 5.8. So the average in case of mild steel is roughly around 5. In case of brass, it's roughly around 5.8. Definitely in case of brass, as it is a softer material, the impression is bigger. Now we can see the chart. The chart. See the chart with 3000 kg load, 3000 kg load and 5.8. Where is the value? 5.8 here. 5.8 means how much? 103. 5.8 means 103. So Brunel hardness number is 103 for brass. Okay. For steel it was 5.5. Two values were there. One is 5 and one is 5.1. So the average is 5.05. So the hardness value is 140, right? So the hardness value is 140. So from the chart we can find out that hardness value of brass is 103. 103 means Brunel hardness number 103. For steel it is 140. So these are the values we are getting. From the sheet, yes, just a minute. From the sheet, okay, we'll take a photograph of the sheet as well. From the sheet, we'll also be able to find out that if we know the Brunel hardness number, we can try to find out how much is the tensile strength of a material. So, hardness is also related to tensile strength, and other thing that is also possible to be calculated from here. So, Brunel hardness number is basically a number, but it can give us lot of information about that particular material. So that's all about the Brunel hardness machine, Brunel hardness testing. Now what we'll do, we'll try to get a copy of this and share with you both the sides. On this side we have the specifications written, what are the different samples, what are the specifications, what are the dimensions of those samples. On the other side we are writing down the values of Brunel hardness number, the values of the radius, the diameter. We are also finding out how much is the value of the tensile strength by using the formula, etc. So both the things will be shared with you, but we should keep in mind that yes, in this case also, we should always take certain precautions. What are those precautions? The sample must be smooth. We should always avoid an impression on a previously existing one. We should always have a good amount of thickness. If the sample is not that thick, probably the results will come out to be wrong. So that's all. We will take the photograph now and share with you. Thank you. এটা ওদের সাথে একসাথে দিয়ে দেওয়া হবে। যদি ব্ল্যান্ড দিই তাহলে একটা প্রশ্ন থাকবে, এটা কি করে হলো, কি করে হলো, এর উপরে দেখলাম সেটা একটা ল্যাবে দেখি তোমরা এক্সপেরিমেন্ট করা তিনটে আচ্ছা। Already we have discussed about Rockwell hardness number and also the Brunel hardness number, the two machines that we are normally using. Okay. Apart from that one, this is another type of machine. We call it a Vickers hardness machine, and this Vickers hardness machine is, I personally feel, it is a little bit more universal in nature. In the sense, it can be used for different types of materials. We can go for small loads, we can go for higher loads, high amount of load, small amount of load. And here, the indenter, already I have discussed about the Rockwell hardness test, where the indenter can be of two different types. We have discussed about the Brunel hardness tester, where we have a 10 millimeter dia indenter, hardened ball indenter. Here we can have an indenter which is of a different type. What is that type? That particular indenter is basically a inverted diamond pyramid. Inverted diamond pyramid. It's not like a diamond braid, it's like an inverted diamond pyramid. Okay, so if I use that particular indenter, right now it is covered with this. Right now it is covered. If I lower it down, I can be able to show you. I am putting my hand at the tip of that. This is basically a pyramid, inverted pyramid, which is a diamond pyramid. And this particular machine is used for different types of material. It can be soft, it can be hard, etc. One more thing I want to mention before I close the whole session. I want to mention one thing. Then apart from these machines, we have this Vickers hardness tester, Rockwell hardness tester, Brunel hardness tester. There are other methods also, like we can use a scleroscope technique, we can use durometer. These type of machines are normally used for measuring the hardness of very soft material. We can have a rebound test as well. These are normally used for plastics and polymers. We are not going to discuss those things in detail, but we are, for the timing, we are just focusing on the macro hardness tests like Vickers, Rockwell and Brinell. Rockwell and Brinell, these two experiments we do in this particular laboratory. Vickers, particularly for post-graduation level and for other purposes, we do the Vickers testing. But all these tests, they are macro hardness tests. Let me just finish this thing with just one word. Apart from this macro hardness test, there are micro hardness tests where the impression will be of micron size. There are nano hardness tests where the impression will be of nano size, nanometer size. Why those particular type of experiments are there? We don't have it. But if we want to have a test done on nano hardness, then what is the purpose? In that case, apart from the hardness, we can know different other properties of that particular material from the result of a nano hardness testing. Similarly, for micro hardness testing, we can get the very, very localized response of a material, very, very localized on the order of its grain size from the machine of a micro hardness tester. For macro hardness testing, it's not possible. It's more or less an average type of response from the surface of the material. Hardness is a surface property. We can find out the hardness of a material by using all these tests to a great accuracy. We can find out the hardness and we can try to correlate the hardness of one material to its various other mechanical properties as well. One more thing, hardness of Vickers, hardness of Rockwell, hardness measured by Vickers, measured by Rockwell or measured by Brinell, all these values are interconnected. So we can convert the Vickers hardness number of a material to Rockwell hardness number, Rockwell hardness number of a material to Brunel hardness number and vice versa. So that is the beauty of these hardness numbers. Hardness can be expressed as this type of Vickers hardness, Rockwell hardness or Brunel hardness number. Also, it can be expressed in a unit which is same as the unit of pressure or stress like GPa or megapascal. So in case of just one example, in case of steel, we often say the hardness of steel we have already measured in Rockwell, it's coming out to be say RC 65 or something like that. In absolute term, in absolute scale, we can call it 2 GPa. So hardness of steel can be 2 GPa. Hardness of steel, if I measure it with a Rockwell hardness tester, can come out to be RC 65 or say RB 87 like that. So all these things are the same thing, but different expressions. So we can express hardness in different ways, either in number or in absolute term like GPa or LPa. That's all. Thank you very much.
Any question regarding the tests?
স্যার
No,
এখন
sir.
তো মানে পুষে পুরোটা সময় হলো না, মানে একবারে এতটা স্যার মাথায় ঢুকলো না, আমি সেটাই বলতে চাইছি। একটু দেখে যদি কিছু হতো তাহলে আপনাকে জানাতাম।
ঠিক আছে, দেখে জানাও। উইকের মাঝে যদি কোনো কোয়ারি থাকে তোমরা ক্লাসরুমেই পোস্ট করতে পারো, আমি চেষ্টা করবো আনসার করার। আর একটা জিনিস শুধু, সেটা হচ্ছে যে তোমাদের ওখানে একটা কনভার্সন করতে দিয়েছে, খেয়াল করেছো কিনা জানি না, আমি দেখাই।
চার্টটা স্যার,
কোনটা?
ওই চার্টটা যেটা দেখাচ্ছিলেন
না,
প্যারামিটারের সঙ্গে।
আরএইচ নাম্বার থেকে স্যার ওই বিএইচ নাম্বার তো এটা?
কোনটা?
আরএইচ নাম্বার থেকে বিএইচ নাম্বার তো? রকেল
না,
থেকে
আমি দেখাচ্ছি কোনটার কথা বলছি। এখানে যে দুটো ফর্মুলা দেওয়া রয়েছে, একটা হচ্ছে ফেরাস অ্যালয়ের জন্য, বেসিক্যালি মাইল্ড স্টিলের জন্য তোমাদের ক্ষেত্রে, আর একটা নন ফেরাস অ্যালয়ের জন্য, বেসিক্যালি তার মানে দাঁড়ায় হচ্ছে ফর ব্রাস ইন ইউর এক্সপেরিমেন্ট। এবার সো ওয়ান্স ইউ হ্যাভ দ্য BHN, you will get the tensile strength, that is the ultimate tensile strength, sigma ut, in tons per square inch. ওকে, এবার সেটাকে তোমাকে তুমি যদি পরের পেজটা দেখো, you'll have to convert it to megapascal, the last column. Okay, so you should be in a position to convert a ton per square inch to megapascal. ঠিক আছে, এখন so you know, first of all তোমাকে কিসে কনভার্ট করতে হবে। 1 ton is a unit of 1 ton weight, ঠিক আছে, so you'll have to convert that 1 ton weight to 1 kg weight, and that turns around 1000 kg force, 1 ton. Now 1 kg force you'll have to convert into Newton, that is 9.81 Newton. Okay, and আরেকটা যেটা ইউনিট আছে আমাদের স্কোয়ার ইঞ্চ, so you'll have to convert that square inch to square millimeter. Now 1 inch is 25.4 millimeter, 1 square inch is 25.4 squared millimeter squared. Okay, once you do that, that means convert ton to kg and then kg to Newton and square of inch to square of millimeter, then you would be having the value in megapascal. Now 1 inch is 25.4 millimeter, so you can directly get the square inch to square millimeter relation. Also 1 kg is 9.81 Newton, so you also know that relation. But 1 ton to kg, okay, that can be a region of confusion. For example, if you take a British unit, that is slightly more than 1000 kg force. It is around 116 imperial ton, as I can see from the internet. It is around 1016 1016 kg force. Okay, so I would suggest you go with this value, 1016 kg force, 1 ton. Okay, so that probably would that is the information that you need to do the calculation part in the Brunel hardness test. So I have shared one entire folder containing all the blank laboratory sheets. I have given you some instructions regarding how to write report. I have already set an assignment for you to submit the report in 7 days, and তোমরা যদি আরেকটু সময় নিয়ে দেখো, হয়তো আমার ধারণা আরেকটু ক্লিয়ার হয়ে যাবে। আমি আশা করেছিলাম মানে আজকেই ক্লিয়ার হয়ে যাবে। এনিওয়েজ, যদি তোমাদের আর কোনো কনফিউশন থাকে দেখে নাও, তোমরা যা অসুবিধা হবে সেটা ডিসকাস করা যাবে। ওকে
স্যার, একটা জিনিস বলছিলেন যে RH নাম্বার